Good afternoon and welcome to NASA's Jet Propulsion Laboratory. We've got a lot to cover today about the Mars Curiosity rover, including some new images and a special message. First, I'd like to introduce our panelists. We're going to hear from Dave Lavery, the program executive from Mars Science Laboratory, and he's from NASA headquarters in Washington. Mike Malin is the principal investigator of the MASCAM, or MASCAM, on Curiosity with Malin Space Science Systems in San Diego. John Grotzinger, Mars Science Laboratory project scientist with the California Institute of Technology in Pasadena. Paul Mahaffey is the principal investigator of the Sample Analysis at Mars, or SAM instrument, with Goddard Space Flight Center in Greenbelt, Maryland. And we have Chad Edwards of JPL, Chief Telecommunications Engineer for NASA's Mars Exploration Program. We're going to start things off with Dave Lavery.
Good afternoon. We've got a special piece of information to talk with you about today. Everyone's very familiar so far with the photos, the data, the spectra that have been returned from the Curiosity rover. We actually have a new data type that we're going to let you hear about today that's a unique first of. One of the things that the rover has returned recently from the surface of Mars is actually a pair of audio files, and we're going to talk about the first one today. This is a message from the NASA administrator that you're going to hear that was actually sent from the rover from the surface of the planet. It fulfills a couple of different purposes. This is an appropriate, first off, an appropriate thank you and recognition from the administrator to the team that put Curiosity on the surface. In addition, it also fulfilled a purpose in helping us exercise some of the new adaptive communications capabilities that Curiosity has in terms of transmitting information back from the planet and getting information to the planet. You're going to hear some more about that from Chad in just a few minutes. But perhaps most of all, it was actually an opportunity to understand that we could have a voice, a human voice, sent back from the surface of another planet for the very first time in history. With this, we have another small step that's being taken in extending the human presence beyond Earth and actually bring that experience of exploring the planets back a little bit closer to all of us and actually extending that human touch. As Curiosity continues her mission, we hope that the words of the administrator will be an inspiration to someone who's alive today, who will become the first to stand upon the surface of the planet Mars. Like the great Neil Armstrong, they'll be able to speak aloud in first person at that point of the next giant leap in human exploration. So if we could have the video, please.
Hello, this is Charlie Bolden, NASA Administrator, speaking to you via the broadcast capabilities of the Curiosity rover, which is now on the surface of Mars. Since the beginning of time, humankind's curiosity has led us to constantly seek new life, new possibilities just beyond the horizon. I want to congratulate the men and women of our NASA family, as well as our commercial and government partners around the world for taking us a step beyond to Mars. This is an extraordinary achievement. Landing a rover on Mars is not easy. Others have tried. Only America has fully succeeded. The investment we are making, the knowledge we hope to gain from our observation and analysis of Gale Crater, will tell us much about the possibility of life on Mars, as well as the past and future possibilities of our own planet. Curiosity will bring benefits to Earth and inspire a new generation of scientists and explorers as it prepares the way for a human mission in the not-too-distant future. Thank you.
And with that, we have the first human voice from another planet. Mike?
Thank you. If I can have the video, please. This is going to be a pan through and zoom into the full resolution MASCAM 34, the medium resolution camera view of Mars. This mosaic has been released a couple of times going through. We filled on all the holes. We've added Mount Sharp in the system in the sequence. This is basically 140 M34 images. The mosaic is about 29,000 pixels wide by 7,000 pixels tall. The colors in this are modified from the original as returned. As returned, it's a little more khaki looking. We basically do processing to brighten up the scene and to adjust some of the colors. As you can see, the layering in Mount Sharp, John's going to talk about that in a few minutes. This pan is going to end at a location where I'll pick up with some stills in a minute. Basically, this mosaic was out of focus. We didn't have the focus positions characterized well enough when we landed to ensure that the images would be in focus when we took this sequence. We've been in the midst of a characterization phase for the last week or so, gotten several hundred images, and these images are going to be returned to the Earth over a longer period of time in a raw form that allows us to do a bunch of tests. Basically the same area you were looking at in the last portion of the video. Just a word about the colors. This has been white balanced, but with a little less blue than normally comes in with white balance. I do this because it looks pretty to me, and it's also a geologically interpretable image. Since my experience is on the Earth, I like to look at things as they would look like on the Earth. And on Mars, it's, as I said, a little more khaki color, a little bit, also a little pink on top of that. In the foreground, you see the gravel lag that the rover is sitting on. Between us and that middle section, which is a rim of an impact crater, there's actually a little depression between us. And as you'll see in a few slides farther on, I've got some of the distances labeled. And then farther out, you see the darker sand dunes. There's actually, in that foreground view, a sort of little orange-brown ripple, which is sand of a different composition than the far middle sand in the darker area there. The next slide shows a box that's just going to, I'm going to bring up that area in the M100. Next slide shows the left side of this image is the M34 zoomed up by a factor of 3. Because there's a factor of 3 difference in the resolutions of the two cameras. On the right-hand side is the M100, the 100mm focal length camera. And again, at these types of scales where you're looking at sort of an average down view as is shown in television, it's very hard to see the improvement in the resolution. But towards the end, I'll show you one thing where I think the quality of what we're getting from the high resolution camera will come through. The next view shows that single high resolution. This is actually two merged narrow angle or M100 images, and we took a whole sequence of these from looking basically from the rover's wheels all the way out to the horizon, running through the entire focus range of the cameras, and we've characterized in great detail now where the best focus at each distance is, and these are in much better focus, and you'll see in a minute the quality when you zoom it up. Next slide will show the distances. So there's a gravel in the foreground out to about 100, 125 meters. Then there's a little swale, which is a depression. From there out to the rim of an impact crater. So there's a depression between us and the rim of the impact crater, and that depression goes from about 125 to 230 meters. And then those rocks are at 230 meters, and they're about a meter across, something like that. You'll see a slightly lighter area just below the 3.7 off to the left. That's the other rim of the crater. That's the far rim of the crater. That's only about another 20 meters, 30 meters away. Between there and the 3.7 kilometers at the base or in the middle of this image, which is on the dune field, the dark dune field, there's a depression that is found completely around Mount Sharp. There's a moat, a deeper area. We don't actually start seeing it until it's about 3 kilometers away. And then you can see mounds at a variety of distances. At the very top of this slide, we're looking 16.2 kilometers away. You're looking through some haze, which is why it gets a little brighter as you go to the top of the image. The next slide is going to be my last. This is an enlargement of that last slide, and it's very geologically exciting to me, and it's also very pretty. It's probably a little bit more pastel and a little bit pinker than it would be to your eye, but it's to me very geologically interpretable, and there's a lot of neat stuff in there that I see. So you sort of see from the middle right side of the image going up to towards the top, there's sort of a diagonal layer. That's actually a layer of material that's draping over previous existing topography, and that whole stuff was then buried and exhumed and eroded to give you what you see now. Last thing, the last slide is for reference. In the box of the main image, which is about 30 meters across, there's a little black dot. That little black dot is a boulder the size of the rover. And so I've enlarged it in the lower right there so you can see it. But that gives you an idea of the scale of these hills and the canyons that we'll be driving on. Basically, this is the ultimate goal. This is where we want to get in the next year and a half or 2 years. This is the place we want to be. This is 10 kilometers away, and it would take the rover, even if the rover were driving flat out, 100 days to get there. And we're not going to drive flat out because we have science to do as well. So it's going to take us a while to get over there, but basically, when we're there, if we had left the camera at the landing site, we'd see this, and it look, maybe we'll get up to that boulder and we can actually see what it looks like. John?
Yeah. Thanks, Mike. I think, Henry, if you could just put that one back up again. I think when those of us on the science team looked at that image for the first time, you get this feeling, that's what I'm talking about. That is why we picked this landing site. And although the anticipated scenic beauty was not something that was at the top of the list for reasons to select it, it was certainly one thing that we were hoping would come through one day. So it's awesome to see this. And I think when you look down from orbit and you get a sense for what you're looking at on the ground, you don't really know what it's going to look like until you're on the ground, and then you see it. The really amazing thing about this is all those layers that you're looking at are the layers from orbit that contain the hydrated phyllosilicates and sulfates. So everything in that image there is a science target for us. And again, the goal here is to drive up eventually, and Mike's right, it'll probably take us a year to get there, but when we do, there's a very systematic approach to exploring, moving around through this terrain that looks like it was something that comes out of a John Ford movie. We're going to be driving the rover around in these valleys and looking up at these hills and finding the places where the strata come down and intersect the topography that the rover can drive through. And we know it can because there's so much great data from orbit that allowed us to simulate the drives before we chose this landing site to demonstrate that we could make it up through this terrain. But as the images came down, there was another feature that really caught our attention. So if we can go to the next one, what you see in this image, in the mosaic that Mike put together, is there's a train of white dots that we placed there to indicate a transition from the strata that are almost flat-lying, not quite, and they're full of the hydrated minerals, to strata above them, which do not obviously contain the hydrated minerals. Now, we don't know from orbit whether they're absent those spectral responses because they're covered with dust or because they're truly absent. But the striking thing about it is that everything above that line of white dots is steeply inclined with respect to everything that's below it. They dip from left to right. And these are features that geologists call clinoforms. They indicate that in the accretion of the strata that they built out progressively from left to right in a relative sense. So this is a spectacular feature that we're seeing very early on that you only had the slightest hint from orbit based on the orbiter data looking straight down. You really need to be down on the ground and looking at a cross-section. But this kind of relationship is something that can help us understand the origin of these strata that clearly are the result of the exhumation of the larger sequence of strata that created Mount Sharp. So the Earth has lessons to teach us about situations like this. And if we go to the next one, we see the Grand Canyon, which we have always felt is a good analog for Gale. This goes back to work that Mike and Ken Edgett did over a decade ago, where they appreciated the thickness of strata that were there based on looking at images from the mock camera. And they also anticipated that contact with the white dots on it not this one, but the one from Gale, may be what a geologist calls an unconformity, where there was some profound change where you go from the lower layers to the upper layers. And here in the Grand Canyon, you have the same thing. All the layers beneath that train of white dots are inclined from left to right, and everything above it is flat-lying. And this is a very dramatic unconformity. It represents a record failure in Earth history of on the order of several hundred millions of years of time. Now, we don't have any way to do an analogous thing on Mars, but by looking at these geometric discontinuities in the strata, we can sense that there is a big change up Mount Sharp, and one day we hope towards the end of our mission to get up and go across that contact and check it out. And so with that, I'll turn it over to Paul to tell us about what Sam's found.
Yeah, thanks very much, John. I'm here really to tell you about completion of what's a real milestone for the SAM team, completing an assessment of the health of SAM. Curiosity, as you've gathered by now, is a very complicated beast with lots of parts, and the project's being very systematic about testing things out, and we're trying to be patient and wait our turn. And our turn is coming now, and in fact we've completed a series of tests that tell us how SAM's performing. Why don't you bring up the first graphic? Before I go into the test, I'll tell you just a little bit, remind you a little bit about SAM and what SAM does. Those images are just spectacular. So Mastcam is kind of the eyes of curiosity, and we think of ourselves a little bit as a nose of curiosity, and we're getting ready to start sniffing. And we sniff both atmospheric gases and gases that we drive off of solids. And the tests that we've carried out up to this point, and the test I'm going to talk about in a little bit more detail is really the fourth test, have been designed to make sure that all these pieces are working. The first test we did was just kind of an aliveness test. We turned on for a few minutes, and Sam comes back with Sam, I am Sam. And we know that we're talking to Sam, but it also gets data on all the sensors. The next test really was to go through a much more comprehensive test. This was some days ago, where we turn on all the heaters and look at a temperature response. It's about an hour-long test. That was fine. The third thing we do is, one part of SAM is this electromechanical system where we process solid samples. We put a sample under the SSIT, the solid sample inlet tube that you see on the right frame there, and it gets shaken. The sample goes down into a cup. We move the cup into an oven. We heat it up, and we sniff those gases with multiple instruments. And so what we did in the third test was make sure that that system was working, and it was working just fine. But we still hadn't turned on our pumps. We hadn't turned on two of the main instruments, the mass spectrometer and the tunable laser spectrometer. So that's what we did. We got the data Saturday morning at 5 a.m., and everything worked beautifully. So it was really a big milestone for the team. SAM is a combination, as I mentioned, of 3 instruments, but then it's glued together with this set of transfer tubes that we heat up, the sample manipulation system that I mentioned, and so on. So it's really a fairly complicated device. We've had many dozens of talented engineers all over the country, and in fact, it's an international effort. The tunable laser spectrometer in SAM was developed right here at JPL by Chris Webster's team. The gas chromatograph was developed in France by Michel Caban and his team. The mass spectrometer was developed at Goddard, and then all this system was integrated and tested at Goddard. So we also had engineers in many states kind of contributing remotely, Michigan, Florida, Montana, red states, blue states, all over the country. So this really was an assessment of SAM's health. And let me talk a little bit about the test then. This test was designed to take a brief sniff of Mars' atmosphere and then put some of that gas in the mass spectrometer and some of it in the tunable laser spectrometer both to look for isotopes, heavy versus light elements in compounds, and to look at the major constituents of the gas. But it was primarily an engineering test, see if them's healthy and if the instruments work. The one little blip we had actually was that we had brought along a little bit more of a combination of Earth atmosphere that had very slowly leaked into the TLS and a bit of calibration gas. And so when we tried to pump that out of the TLS, the pump current went up a little bit and did what it was supposed to do. It said, I'm not too happy with that current, and it shut itself down. But as a consequence of that, the very first sample, we did not measure Mars atmosphere. We measured Florida air and our calibration gas, which was of quite less interest to the science team, but nevertheless, we had a really good exercise looking at how the instrument worked. So in summary, the instruments work beautifully, the TLS and the mass spectrometer. We still have to wait for tests of the gas chromatograph. That'll come some sols down the road. And we're looking forward in a few sols really to getting our first sniff of Mars atmosphere and learning more about the history of Mars, what the atmosphere is telling us with regard to its isotopes and its composition, and then ultimately how that compares with gases that come out of rocks. So that might have been formed billions of years ago. So it's really going to be fun. We're looking forward to getting in those layers that John and Mike talked about. And with that, I'll hand it over to Chad, who's going to tell us about how the data all comes down and gets processed.
All right, thanks, Paul. Yeah, I'd like to share today a little bit of the story of how we bring the kinds of science data that you're hearing about today back to Earth. One of the challenges of a landed mission, even for a rover the size of Curiosity, is the daunting job of transmitting data from the surface of Mars all the way back to Earth, which can be up to 400 million kilometers away. A rover like Curiosity has a relatively limited capability to transmit on that direct-to-Earth path. It has a transmitter about 15 watts and an antenna about a foot in diameter. And with that capability, trying to communicate straight back to Earth, we're limited to data rates on the order of about 1,000 bits per second. And that's just not adequate to bring back the kind of science products that we're looking at today. And so what we've done is take advantage of the orbiting science satellites that we have around Mars and use them as relay communications assets. And essentially we have a telecommunications network around Mars that's allowing us to bring that data back. If I could have the first chart, please. We have 3 orbiters at Mars today. The Odyssey spacecraft that was launched in 2001, ESA's Mars Express spacecraft that was launched in 2003, and NASA's Mars Reconnaissance Orbiter launched in 2005. All 3 of these orbiters were positioned on landing day to collect signals from MSL as it landed during the 7 minutes of terror of entry, descent, and landing. It was very important for us to capture that critical event telemetry, and we took advantage of the unique capabilities of each of these orbiters to capture information about the landing. Since we've landed, we've typically been using our NASA orbiters, Odyssey and MRO, to do the bulk of the data return, and I'll show you in a second a little bit about why their orbits are particularly well suited for supporting the surface mission. But a very important aspect of our strategy is the ESA's Mars Express spacecraft is available as an additional backup relay asset, and that's an important part of the robustness of our telecommunication plan. And we have had a successful opportunity already on Sol 13 to demonstrate that we can flow data through Mars Express and back to Earth. Okay, if I could have the next chart, please, and this will give us a little bit of a view of what these orbits look like at Mars. You're seeing Odyssey and MRO. They're in orbits of about 300 to 400 kilometers, and you can see as MRO passes over the landing site, it establishes a link. These orbits are sped up. These relay contacts last for about 10 to 15 minutes, typically. You can see the orbit planes are fixed in orientation in a polar orbit, and they're actually, our 2 orbiters are positioned, MROs around 3 p.m. and 3 a.m. local time on Mars, and Odyssey's about 4 p.m. and 4 a.m. And you're looking at the afternoon side of the planet here. So typically we have a relay opportunity with each of the orbiters in that afternoon portion. You also saw the highly elliptical orbit of Mars Express in that visualization. Now we're down on the surface, and this gives you a little bit of a view from Curiosity's perspective about what a relay pass looks like. In particular, on this link to Mars Reconnaissance Orbiter, we have a new capability which we refer to as adaptive data rates, so that as that orbiter rises in the sky and the quality of the link improves, the 2 radios at each end of the link are able to exchange messages with each other and optimize the data rate as a function of time over the pass to constantly be using the maximum data rate that the communication channel can support at that point in time. It's the first time we've exercised that. Over the weekend was the first time we had a chance to use that. It performed fabulously. We set a record for the amount of data we were able to bring back on a single pass, even though that pass was not at a particularly high data rate or a particularly high elevation angle. And so that really bears out the strength of this adaptive data rate algorithm to be able to take advantage of the geometry of the pass, vary the data rate continuously as you fly across the sky and move a large amount of data. So just to conclude, if I could have the last chart, and this is sort of how we're doing to date. We're looking at 20 sols here, and you're seeing a chart of the cumulative volume of data that we've returned from Curiosity via the 2 NASA orbiters. Again, we've only had one short relay pass that we've conducted with Mars Express. That was very successful in terms of demonstrating our interoperability, but not a significant contributor to the total amount of data volume that we've brought back to date. And you can see that to date, we've already brought back in excess of 7 gigabits of data. Just by contrast, that's about a factor of 2 to 3 more than we had brought back from Spirit, Opportunity, or Phoenix at that same point in the mission, 20 sols in. And that's really a tribute to particularly the new capabilities on the Mars Reconnaissance Orbiter spacecraft, where we have what we call an electro radio on each of those orbiters, on MRO as well as on MSL. It allows us to go to much higher data rates, instantaneous rates of up to 2 megabits per second, and this adaptive data rate capability that allows us to bring a lot more data back. So I think at this point, I'll hand it back to Jane.
Thank you very much, and we'll start our Q&A period for reporters. We do have some reporters who are calling in with questions today, but let's take a look and see if anybody here at JPL has a question. If you do, please raise your hand and wait for the mic to come to you, and then state your name and your affiliation. First question, Emily.
Emily Lochtawala from the Planetary Society. I have a question about the geology in the hills that you're looking at. The comparison that you made to the Grand Canyon showed an angular unconformity where the beds were angled, chopped off, and then you had flat-lying beds. I don't know if I've ever seen anything where the beds on top were inclined. So can you talk about the kind of environment that might have made that sort of bed form?
It's a really good question. The layers are tilted in the Grand Canyon because of plate tectonics here on Earth, so it's typical to see older layers be more deformed and more rotated than the ones above them. In this case, you have flat-lying layers on Mars overlain by tilted layers, and you know, the science team, of course, is deliberating over what this means. But in the absence of plate tectonics, I think you're really kind of pretty much looking at some kind of a mechanism that relates back to the physical environment in which the strata accumulated, and you know, we don't have too much more insight into that right now. But it does require a flux of material, presumably from left to right in that image that you're seeing there. So it somehow relates to the depositional mechanics, we would guess. Yeah.
And if I could just ask another quick question of Mike. First of all, that picture was stunning, so congratulations on the performance of your camera. The mosaic is really, really beautiful, but there's one missing part to it, the rover at the bottom, and I'm wondering if you're planning on taking a mosaic that will include the rover in color as well.
Not likely. It's not part of our requirements, so it's bits you have to bring back and it's planning you have to put into it. I'm not sure exactly how many more mosaics we're going to end up getting once we release the camera to the science team. They're going to want to go shoot lots of special purpose targets, I think.
Thanks.
Okay, do we have any more questions here at JPL? If so, please raise your hand. All right, why don't we jump to the phones now? We have a question. Let's take a question from Irene Klotz at Reuters. Hello, Irene.
Hi, thanks very much. I actually have a couple questions. The first probably for Chad regarding that, the relay broadcast of Charlie Bolden's voice. Could you just explain if this was some technical accomplishment, or could this have been done before with other rovers if someone had thought or had wanted to do it? I guess I just really didn't understand beyond kind of the PR value what it is that you were demonstrating.
Okay, my understanding is that the volume of data in that audio file is on the order of about 4 megabits. That's certainly something that, a capability we could have executed in the past on prior missions. I think the growth in our data transmission capabilities on this mission allows us to do this while also not sacrificing any of our science bandwidth. So yeah, that would be my thoughts on that.
Okay, thanks very much. And for John, I just wanted to follow up a little bit more about the angles that were demonstrated in that picture. Do you have some measurement of the non-conformity? In other words, what's the angle of the top layers compared to the flat ones? And is there anything on Earth that forms things like that aside from the plate tectonics that you've already discussed?
Yeah, we will eventually get to measuring those angles. Mike has been working on sequences to execute that give us long baseline stereo, and then from that we should be able to actually quantitatively determine the angles up there. Again, you know, on Earth there are a whole host of mechanisms that can generate inclined strata that have only to do with the depositional mechanics of the process itself. If, for example, you took a cross-section through a volcano, all the layers would be dipping at a steep angle that would be corresponding to the surface of the volcano, if it's volcanic material. You could imagine other situations where sediment gets dumped down at an angle and that are subaqueous in origin. The wind does that every time it makes a sand dune. You have strata that dip at the angle of the front of the sand dune. So, you know, the cool thing here is just that the cameras have discovered something that we were completely ignorant of prior to that. It's a non-unique interpretation. It's going to take the science team a lot of work to get at it, and probably we're going to have to drive up there to see what those strata are made out of. But a lot of people ask the question: are there big surprises that since you've landed that you see? And so far it's kind of looked like terrains that we're familiar with and things like that. And this thing just kind of jumped out at us as being something very different from what we ever expected.
Thank you.
Okay, John, I understand we have something that has just come in, a picture that we wanted to share with our audience.
We just had, this is late breaking news. This just came in down from Mars in the last hour, and it shows the tracks of our most recent drive. And this is the result of the first drive that was commanded explicitly for the purpose of science. And it positions the rover directly over the most prominent of the scour marks that was created by thruster impingement during EDL. So if you go all the way back to the time when we first landed, I made the comment about how we've basically blown away all the surface materials and we get kind of a freebie sample. Well, now we're sampling it with the DAN instrument, which is the neutron generator, and that will acquire data over this bare rock to compare with measurements that were made where the soil cover existed. And the science team has also planned observations with the ChemCam instrument on that scour mark as well. So we're going to be collecting quite a broad range of measurements over this feature before, in a few days' time, we drive away to the east towards Glenelg.
Thank you, John. It's always fun to have breaking news in a live news conference. Let's take a question from the phone. Leo Enright with Irish TV.
Thanks, Jane. Just looking at that picture, it's obvious you can see the wheel tracks almost like footprints. And I think for the European audience, it's late at night. It'll be tomorrow morning, really, when most people get to hear this. But they're still thinking of Neil Armstrong. And I'm thinking maybe John and Mike particularly, because you've devoted so much time as explorers on Mars. When you look at these wheel prints, how do you connect those with the boot prints that Neil Armstrong made all those years ago?
Well, I think the analogy is really a terrific one, because if it's not in this image, but if you go back to some things we've released already, you will see what I think will be an iconic image of the mission, where you see the 4 scour marks made by the thruster impingement with wheel tracks that basically begin from nowhere. So you know a spacecraft sat down, the rover was dropped onto the surface, and you see this track back to the origin. And now what we're seeing here is the results of tracks involving the first motions of the rover. But I think, you know, instead of a human, it's a robot pretty much doing the same thing.
All right. Our next question is going to come from Todd Halverson at Florida Today. You with us, Todd? Maybe we'll have to get back to Todd. He may have been, something happened. Okay, our
Jane,
next.
I'm here. Can you hear me now?
Oh, yes. Hi, Todd. Go ahead with your question.
I'm sorry, I pushed the wrong button on the telephone. I'm wondering. I'm looking at these pictures and listening to Charlie Bolden's voice, and I'm wondering if somebody can talk about the significance of beaming back a human voice from another planet. And you know, I think about the times when I was a kid and I would hear voice transmissions from the moon back to Earth. So maybe you can distinguish this as a first for a planetary mission rather than a mission to the moon. Is that your point? Thanks.
Yeah, I think you hit the point exactly, that this is the first time that we've had a human voice transmitted back from another planet. Obviously, in the case of Neil Armstrong and his famous quotes from the surface of the moon, we do have that statement made by a human present in the location where it originated. We aren't quite yet at the point where we actually will have a human present on the surface of Mars to make those first words yet, but this represents the first opportunity to actually have a human voice that is transmitted back from the surface of a planet beyond our own, and that is really the significance that we attach to it. And we do recognize that this is a data file that was sent up to the rover, stored on board, and then sent back from the surface of Mars. And so although it's not quite the true first-person representation of humanity's contact with the surface of Mars, it is a small step in that regard. It's an opportunity to extend the human presence virtually and in some small piece out beyond our own world and have that represent the eventual human mission to Mars that will be the follow-on to the robotic precursors missions that we're doing right now.
All right, before we go to our next question, I understand we have yet another image and possibly a couple of images, so let's bring up the first image.
Yeah.
John, do you have anything you wanted to comment on?
Yeah, what you see there is obviously wheel tracks crisscrossing each other. And I believe if you look to the upper left, that's probably close to where the rover started out. And then you see tracks angling down towards where the wheels are now that are crisscrossed by the tread marks. And the cool thing about it is actually right where they're crossing, you see the imprint of the what is now known to be Morse code for JPL, and that imprint, of course, is used to assess wheel slip, and that indicates one revolution around the wheel every time you see that thing stamped on the surface. And so, based on how closely compressed those marks are, gives the engineers, the mobility engineers, a chance to assess the properties of the terrain in terms of how mobile the materials are.
Okay, well, folks, as I said, this is live stuff coming in, so that's kind of fun today.
Mount Sharp in the background.
Okay, thank you. Next question is going to be from space.com and Mike Wall, who's on the phone.
Hi, this one's probably for John. Could you just give a little more detail? How much time do you think you guys are going to spend at those scours doing those investigations? And yeah, when do you think that you might head off and might kind of make your first big drive toward the science target?
Yeah, it begins tomorrow. Tomorrow we do a bump of, Mike, 10 meters? Yeah, 10 meters. And then Mike will be set up to acquire the second part of his data set to demonstrate the technology to use long baseline stereo with the mass cams, which is going to be terrific. And then after that, we start driving, and the rover engineers are really excited about this, the rover planners, the mobility engineers, the guys that drive the rover, and they will execute a series of increasingly long drives that will take us in excess of 100 meters away from the current location, which is what we estimate to be the area that was affected by the thrusters during landing. And so we want to get out beyond that zone of influence and head out across the plains to the east as quickly as possible.
I think we maybe had another question here at JPL. Let's get a mic back to Emily here in the second row, please.
Question here at JPL. Get a mic back to Emily.
This is a question for Paul. I'm wondering, when you do get a chance to sniff the Martian atmosphere for the first time, are you going to be able to read from that results, measurements instantly, or is your instrument the kind of thing where you're going to have to calibrate it for a long period before you're going to be able to say anything definitive about the composition?
Yeah, we certainly calibrated the instrument well before we left planet Earth, and we have some calibration gases along. So I think, quite rapidly we'll be able to establish some of the measurements that we're interested in. The major composition of the atmosphere was measured by Viking, and it was optimized for a certain set of tasks, and we're very interested in doing a double check on that. The new capability that's, aside from the chromatography and looking for organics in rocks and so on, which don't have anything to do with the atmosphere, the new capability that we bring to the atmospheric measurements really is the precision measurement of isotopes with the tunable laser spectrometer, and also our search for trace methane. Obviously, methane's of great interest to us and many other people, but we're going to just be very careful and look at those results and make sure we understand them very, very well before we start advertising something that we may not have. So some of the results, I think, will come early, and others will come a bit later.
And I'm just wondering if you can be a little bit more specific about about what caused Sam to quit an intake of Mars gas.
Yeah, sure. So it turns out we have these miniature pumps. We call them wide-range pumps, but they're really turbomolecular pumps on top of a molecular drag stage. The really nice thing about these pumps is they exhaust naturally right at Mars pressure, at 10 millibar, 7 millibar. And it turns out that there's a very slow leak into the tunable laser spectrometer. And so there was just a little bit of residual atmosphere in there, and in the Harriet cell, which is a cell where the light bounces back and forth to get a long path length for the methane, the carbon dioxide, and the water measurements. And so the few tens of millibar that we had in there, I think we had 51 millibar, and we had assumed that the pump would be fine evacuating that. We routinely evacuate Mars ambient out of the cell, but it was just high enough that the current sensor on the pump said, no, this is a little bit too high, I'm going to turn myself off, and it did. But SAM continued merrily along its measurement path, assuming that we had not turned off, and so we measured that gas. With both the mass spectrometer and the tunable laser spectrometer, it really led to some excitement. The TLS team, Chris and Greg, their eyes were wide open. They saw all this methane, and it turns out it was terrestrial methane, but it really was kind of a good test because they saw that their spectral range was calibrated. The lines were right in the middle of this very, very narrow bandwidth area that they scan. And so in the end, they're really happy. I mean, it's an additional piece of information that we secured with this test. So all in all, we're not too unhappy.
Okay, we're going to go back to the phones. We have a couple people who've been waiting patiently. Thank you for that. We're going to take a question from Ken Kramer of Spaceflight Now.
Hi, thank you. Spaceflight Magazine. For Mike Malin, I have a question, please. Can you talk a little bit about the focusing ability of the cameras? How much do you have to intervene, and how much can the rover focus itself at these close and far distances, please?
The camera has autofocus. Each camera has its own autofocus, except for Marty, which is fixed focus. The mass cams are autofocus. They can focus from, the mass cam 100 can focus from about 1.6 meters out to infinity. But we needed to know the motor count of infinity. And our initial work, we had set the range of where infinity ought to be to a little less than we should have. And this particular test that we did in the characterization let it go, if you will, beyond infinity. And so we got to the other side of the focus range, and then we can actually determine the actual focus position. And we were about 10% off in our initial calibration information. And so, and the rover can do this, or the cameras can do this. We just commanded autofocus. We tend to want to give it a seed number, which is as close as we think the focus may be, and then we scan through in one direction only through that, and we hope to find the best focus, and we fit a curve to find the best focus from the quality of the images that we're getting as we go through the focus position. And that's the save motor counts, because these are mechanical systems, and all mechanical systems in space have a finite lifetime. So we don't want to use a lot of mechanism motion to find the focuses.
All right, we have time for a couple of more quick questions. Lee Reynolds from redorbit.com.
Hi, guys. This question is for Paul. Will SAM be capable of one day giving us an idea of what this area of Mars smells like?
Of what this area of Mars was filled with? Smelled like. You know, we're looking for evolved sulfur compounds from rocks, and you know, depending on most likely it's very oxidized and might be sulfur dioxide, but you never know. So I think that certainly with the variety of chemicals that we hope to obtain from our evolved gas measurement that may have been captured billions of years ago, I think the answer is certainly yes.
All right, thank you.
Okay, back to JPL. Bill, did you have a question?
All right, thank you.
In the second row there. Let's get the mic to him. Okay. I thought you did. I just wanted to make sure.
Thank you. First of all, congratulations again, everyone. These are spectacular images. But I was just wondering, this question of methane is a deep one. Is it isotopically different, the sample you took with you, than what you're going to be smelling for? Like you're looking for a different isotope of methane?
Yes. The methane measurement, even with the very, very sensitive TLS, is very, very difficult because the predicts are kind of on the order of parts per billion. Mm-hmm. And, you know, there's some measurements from Mars orbit. There's some ground-based measurements which are very difficult because you're looking through the Earth's atmosphere and have to do all sorts of correction. But nevertheless, these numbers are very, very low. They're on the predictions, the observations, which we'd like to confirm or not, are on the order of several parts per billion. And so with our direct measurements, we hope to secure that answer. But the isotope measurement of carbon-13 to carbon-12, for example, which is the next thing you want to do, we won't do unless we have several tens of parts per billion in the atmosphere directly. What we have long-term is a plan to really pump up the methane in the TLS using chemical separation in our gas processing system. So that's something that over a period of months we'll be testing out in our test bed at Goddard, which is a SAM, just like the one that's roving across Mars. And anything we want to do on flight SAM on Mars, we do on the test bed first to validate it. And so even if we only have a few parts per billion, we'll be hoping eventually to get the isotope numbers.
So can we compare that to what was possible with the instruments on Viking? Or is it orders of magnitude?
We certainly can. And that's really one reason for the tunable laser spectrometer. It turns out that in the mass spectrometer, you have a hot filament, and just the diffusion of gases out of the hot metals tend to make just a little bit of methane. So it's very, very difficult with a mass spectrometer directly at those levels unless you're using some enrichment technique. If it's much higher, it's no problem. We went to Jupiter with Galileo probe and found methane no problem, but it's very abundant. But at Mars, that's exactly the reason we have the tunable laser spectrometer that Chris Webster and his team developed.
Okay, and we have time for one final question. Leo Enright, back to Irish TV, but can you please keep your question really brief so we don't run over?
Thanks, Jane. I appreciate this. I'm looking for a soundbite, really. It's late at night in Europe, late at night on Mars. When it's morning in Ireland, it will be morning at Gale Crater. And I'd like somebody to be a little bit poetic and tell me, for our breakfast television audience, what will morning look like on Gale Crater now that we've seen these wonderful pictures that you presented tonight?
Come on, John.
You're the poet, John.
No pressure. Geez.
We're not poets.
Yeah, I think you know, the first light image at this particular place is just it's going to be inspiring. We've wondered about this place for years from orbit, and this image is basically looking what direction, Mike?
Southeast, southwest.
Yeah, southwest. It'll look shadowy and beautiful.
Okay, thank you very much, everybody. Oh, I'm sorry, did somebody?
I was going to say, just the one thing maybe you could add to that, given the first measurements from Sam, the images that we have and the audio files that we have, this is the first time we have the sounds, the sights, and the smells of Mars.
That's good.
All right, on that note, we're going to wrap up today's news conference, and a reminder that if you stay tuned, we will be replaying the visuals that you saw today. And there's lots of information and images online 24/7 at www.nasa.gov/MSL. Thanks for joining us today.